Amplitude for finding a harmonic oscillator, or the amplitude of going from one position to another, right?
It's the amplitude to go from one position to another at time t.
And we could do this like classic quantum mechanics thing, like Schrodinger's equation. You can do the same thing, right?
Yeah, you could do it with Schrodinger's. Well,
Get the same result.
Well, Schrodinger's equation. I mean, if you do the time-dependent Schrodinger equation.
Yeah. Okay. It just seems. I don't.
Any other questions?
When we were calculating this in quantum mechanics, we just used some approximation, right?
You did. You didn't do it exactly.
What do we use?
The Fermi golden rule like that, we derived that.
Well, anyway, this is exact.
That's fine. We can do it that way too.
Okay, let's now do this harmonic oscillator in imaginary time, or effectively the thermodynamics of the harmonic oscillator. And you know, if anybody still is hungry, there are several pieces left. Okay, so what are we computing now? Q double prime e to the minus k to h q prime. And this thing is the path integral e to the minus the action, which is 0 to beta, and then it's 1/2 m q dot squared plus 1/2 m omega squared q squared dt, and then of course big D q. And the classical action, of course, is the one you know. SE of Q is integral 0 to beta. Well, it's just this thing. It's just 1/2 m q dot squared plus 1/2 m omega squared q squared dt. Okay, so that's what we're doing. Now, what we want is to find the solution, or the so to speak thermoclassical path that makes the biggest contribution here, subject to the condition that it actually goes from q prime to q double prime in imaginary time beta. Okay, so it has to do that. Otherwise, you could get just 0 for this thing just by having q equal to 0 and let it sit there. But it has to go from q prime to q double prime in time beta. Okay, so what we have to do is we have to minimize this, and that means that we, one way of thinking about it is the variational derivative. In fact, I think I was going to do it a different way, but I think I will do it the variational derivative way. The variational derivatives are spread in chapter 15 of my book. Maybe I can put chapter 15 on the web page. Anyway, it's this. Let's see what the change in SE is for some Q. I call it a Q Euclidean instead of a Q classical. And so we have, so I'm going to have a function here, a functional of two functions. That's the, so to speak, careful way to do variational derivatives. And this careful way actually is clear, whereas the way that physicists usually do it in books and classes is quicker, but it leaves the mind dirtier. And it's just not very clear. So let's just see what this is. This thing, I'm thinking of this not only as the functional, not only as, this is a functional, but the delta means it's actually the variational derivative. And this is a d by d epsilon of an integral 0 to beta of 1/2 m. And then what we have here is q Euclidean dot of t plus epsilon h dot of t squared plus 1/2 m omega squared q Euclidean of t plus epsilon h of t squared, no, the square is out here. And we're taking this derivative at epsilon equal to 0. Okay, so what have we done here? What we've done is we've said we're adding to Q, the Q Euclidean thing we're looking for, we're adding an arbitrary path, and we're multiplying it by an infinitesimal. So h is arbitrary, epsilon is tiny. And we take the derivative. Well, this derivative, of course, is just 0 to beta. The 2 cancels, we get an m. Q Euclidean dot of time, h dot of time, plus m omega squared Q Euclidean of time, h of time dt. And we set this equal to 0, but there was a proviso here. This h is something that vanishes at the 2 endpoints because, after all, we're talking about a path that goes from q prime to q double prime. So that means we can integrate by parts without any trouble. All right? I see a frown. All right, so we integrate by parts, and we get 0 to beta minus m q double dot Euclidean at time plus m omega squared q Euclidean of time times h of time dt, and we're setting this equal to 0, and that tells us what the differential equation for q Euclidean is. And now you see that the m cancels, and what we get is that q Euclidean double dot of time is omega squared q Euclidean of time. Okay, so it looked like the harmonic oscillator, but it's got the wrong sign. So it's just sort of it's an imaginary time, basically. And but the solutions are very simple, obviously. It's QE of t, A into the omega t plus B e to the minus omega t. So the solutions are pretty simple. Okay, because you take the second derivative, you just get an omega squared, and that works fine. Yes?
What terms did you leave out in that second equation after you took the derivative?
This one here?
Yeah, I feel like you should have some more squared.
Oh, of course. Well, we're taking the limit. First of all, we're taking the derivative
Right.
with respect to epsilon. At epsilon equal to 0.
Oh.
So the epsilon squared term goes away.
Okay. That's
Great question, though. Do you have room for a candy or not?
I already have one in the back up.
By the way, I just thought I'd mention something to you. The water department here, several years ago, stopped fluoridating the water in Bernalillo County, presumably due to Republican pressure from the Tea Party and various other intellectual primitives. And the excuse they gave was that, well, our fluoride isn't that bad. It's 5 milligrams per liter, or micrograms, I forget which it is anyway. And the EPA recommends 7, so that's only off by 40%. Well, 40% is a lot, and I'd encourage every one of you to complain. Yeah.
So you're saying you don't use the fluoride-free toothpastes?
No, I always use fluoride toothpaste.
Oh.
Yeah, that's not enough. And this is especially true, and now I'm speaking to the 2 women in the audience. If you have kids, they need to drink fluoridated water. So they grow big teeth, and strong teeth. Yeah. The EPA, in fact, the CDC says that the fluoridation of water is one of the 10 most important advances in public health in the last 100 years. Another one was the chlorination of water.
I think fluoridated water is a small problem to be considering there was jet fuel that leaked into our aquifer. So I think we need to pick our problem.
All right, look, I'm not in favor of jet fueling the water, okay? That's a separate issue.
Just saying, pick your battles.
In fact, the problem is probably not jet fuel in Albuquerque. The problem in New Mexico water is naturally occurring arsenic. And arsenic is really bad stuff. And the reason I say it's really bad is that I keep going off on these tangents. Richard Wilson of Harvard has been one of the people trying to convince the public, although it's useless to convince the public unless you have $100 billion for publicity. Trying to convince the public that nuclear power is safe and much cleaner than coal, obviously. Anyway, but he said to me once that arsenic was really dangerous. And so if Wilson says arsenic's dangerous, whereas nuclear power, he just blows it off, then you can see arsenic really is a problem. Okay, anyway, so this is our Euclidean solution. Let me say what the path is. Well, obviously we have to choose A and B in order to get the right, in order to satisfy the boundary conditions. And those boundary conditions are that A is Q double prime e to the minus omega beta minus Q prime e to the minus 2 omega beta. And this is divided by 1 minus e to the minus 2 omega beta. And B, it turns out, is very simple. It's just Q prime minus A. And now what you can do is you can take this formula, which is very simple, and then with these two values of A and B, and shove them into this formula here, do the integration, and then you find out what the actual classical action is of this what the classical action then is of this minimum, so to speak, minimum energy solution or minimum action solution. And what you get is that the classical action then is 1/2 m, well, it's S of QE, I think. I don't see why it's SE of QE. Well, all right, E for Euclidean. It's 1/2 m omega times A squared e to the 2 omega beta minus 1 minus B squared e to the minus 2 omega beta minus 1. Okay, so that's the value of the, so to speak, classical Euclidean action for the path of minimum Euclidean action. Since the thing is quadratic, the Euclidean action of an arbitrary field QE, or arbitrary field Q, is the Euclidean action of the minimum field plus the Euclidean action of some loop field where delta Q goes from 0 to 0. And so this is just going to be a function of beta. And so we get as a semifinal answer, namely that Q double prime e to the minus beta h Q prime is then e to the minus SE of QE, SE of QE being this thing, times some loop function of beta. And now we can learn, we can find out what the ground state wave functions are if we let beta go to infinity. And what happens then is that this thing is e to the minus beta E0 Q double prime 0, 0, Q prime, where 0 is the ground state. So I've inserted here a complete set of states, e to the minus beta En, and taking the limit beta goes to infinity, all of them go except for this one. So we've got that is equal to this, And we don't even need L of beta because it doesn't involve Q. We see what this involves, it's this. And so the A and B depend upon Q prime and Q double prime. You substitute in there, what you find is e to the minus beta E0, Q double prime 0, 0 Q prime equals L of beta E to the minus a half m omega Q double prime squared plus Q prime squared. And so this tells us that 0Q is e to the minus a half m Q squared times some normalization factor, and the normalization factor is m omega over pi h bar to the 1/4. Okay. All right, I think we can stop there. Sorry for going over a couple of minutes. Any questions? Okay. Somebody must be hungry. All right, let's